This video is on section 7.3 notes, vectors. So at this point in our course, we've learned quite a bit about trigonometry. And even though we're still in a section or in a chapter, the section that we're moving on to feels a little bit like we're switching gears. So talking about vectors is moving on to like a specific subject within math where trigonometry plays a big role. So here we're going to define the difference between scalar quantities, which we've worked with a lot, and vector quantities, which is going to feel a little bit different. Not necessarily new. You might have some limited experience with it in other courses or maybe a little bit in math, but it's going to maybe not feel as comfortable. So scalar quantities are quantities such as length, area, volume, temperature, and time, and those are characterized by a single number. And that number's their magnitude, like their size. Vector quantities are quantities like velocity, acceleration, and force, which are characterized by both a magnitude and a direction. And they're represented with directed line segments. And so in this case, we would say kind of like they're represented with two dimensions, where there's like a line segment that has a length, but it also is facing a certain direction. So the magnitude of the vector is the length of the vector that kind of represents the force, or that represents the velocity, like the size, the number that's happening. And then the direction is the position of the vector combined with the arrowhead on one end of it. And that kind of shows you maybe an angle that it's working towards, or if it's working forwards or backwards or something like that. Equivalent vectors are two vectors with the same magnitude in the same direction. And a zero vector is a vector with no magnitude and no direction. I put a note here, vectors are denoted different ways depending on the textbook that you're using. So it can be a V with kind of like a little half arrow. And so that if you write it, looks like this above it, a V with an actual arrow above it, or a bold V. I don't really like the bold V personally, because how do you write that if you're the one writing it out? But in print, it makes a little bit more sense because you don't have to use math type to do it. So this is the one that I like to write when I'm putting my answers. But this one right here, the bold version, is what your textbook uses. So I just wanted to give you a heads up so that you'll kind of recognize it when you see it. So first we're going to talk about scalar multiplication. So we have, and this is going to feel a little bit intuitive because it kind of makes sense. So here we have a vector. It has this is vector A. It has a length, and it's kind of going up at an angle, slanted up to the right. So if you talk about a vector that has a scalar multiplier of a negative 1, then the vector would be the same length, it would have the same magnitude, but it's negative, so it would go the opposite direction. You can see it's got the same slant to it, but the arrow goes the opposite way. Here, if we have 2a, we're going to have that magnitude, that length has been doubled, but the direction is going the same way. Here, if we have 1/2 a, we can see that it's still going the same direction, but now it's half the length that it was before. Negative 2/3 of a is now going the opposite direction because it's negative, and it's 2/3 of the length. So here it says to find the vector 3/2 a, and so we know that we're going positive, so we're going to go in the positive direction. We're not going to do it opposite, and we want to have 3/2, which would be 1/2. So I'm going to say this is 1/2 of vector a. And so, and you can eyeball this. So I'm going to say here is, oh, that looks like vector A to me. And then this little bit looks like the 1/2. And so this is just me showing my work. This is A, this is 1/2 A. And so I'd say this vector right here is 3/2 A. So that's what scalar multiplication looks like in vectors. All right, vector addition is a little bit different because we have to keep in mind not just the length of the vectors, but we also have to keep in mind what direction they're going. So what angle they have that's kind of like they think of it or they talk about it in vectors as the horizontal component. So how far is the vector going to the left or right? And then the vertical component, how far is the vector going up or down? All right, so to do vector addition, we have this definition right here, and it's really kind of a set of instructions telling you what to do. So it says to find the resultant, or the sum, a plus b of any vectors a and b, position b without changing its magnitude or direction, so that the initial point of b coincides with the terminal point of a. So what we're going to do is we're going to draw a first. So, and I'm going to put it, you'll see why in a second, but I'm going to draw it down here. So it's pretty horizontal, and looks pretty good. So there's A. And then position B without changing its magnitude or direction, so that the initial point of B, so the starting point of B, coincides with the terminal point of A, the ending point of A. So we would say that this is the initial point, and this is the terminal point. Okay, initial point, terminal point. So, and then we're going to go ahead and draw B. Going to try to have the same slant to it. Okay, so there's B. All right. The vector that begins at the initial point of A and terminates at the terminal point of B is the vector A plus B. My high school teacher called this the tip to tail method. So in vectors, this is called the tip or the arrowhead of the vector. This is called the tail of the vector. And so when you draw the vector, you draw from the tail over to the tip, and then the tip starts with the tail of the next one. And then the tail goes to the tip, and then you start with the tail goes to the tip. So I don't know if that helps you, whichever way helps you, but we draw A first, and then B, and then this is A and B. And if you notice, the way that this works is A has this much horizontal movement, B has like this little bit of horizontal movement, and A plus B has all of that horizontal movement. Vector A has like no vertical movement, B has all this vertical movement, and so A plus B has that much vertical movement. So you can kind of see that A plus B, even though it's a weird way of adding something together visually, it kind of makes sense because it includes the horizontal differences and the vertical differences. We can also always do the reverse of this, right? Because when we add things, A first and then B would give us the same result as if we took B first and then did A. So if I started, I'm going to do a different color here. If I started with this and I drew B first, and then where B terminated, I started vector A. And then I drew my resultant. So from B to A, then this would be the resultant B plus A. And B plus A and A plus B are about the same. Well, exactly the same. And so what happens is you make this little parallelogram where if you do the first one and then the second one, you get one resultant. If you do the second one and then the first one, you get a different resultant. But together it makes a parallelogram. All right, if we look at the next page, I kind of mentioned this already, but it says a non-zero vector is the sum of its horizontal and vertical components. So I kind of already mentioned that we've got the horizontal and the vertical components, but now they're getting a little more specific. They're saying that a vector is the sum of its horizontal and vertical components. So if we have this vector here, then we could really say, well, to write this vector here, you could have a perfectly horizontal vector, You could call that wx, and you could have a perfectly vertical vector, you could call that wy, and if you were to add that perfectly horizontal vector and perfectly vertical vector together, you'd end up with this kind of diagonal vector. And then because we are adding vectors together, we end up getting the sum of those vectors that we added, that's the resultant. And we put them together, they have horizontal movement and vertical movement, and so that's what makes it diagonal. All right, so we're going to get a little bit deeper into this. As you can imagine, if we're talking about vectors as directed line segments, where we're talking about a force that goes in a certain direction, or velocity, which kind of feels like speed going in a certain direction, or acceleration going in a certain direction, then that can be drawn anywhere to represent anything. But what we do often is we take vectors and we draw them as position vectors. We put them in a coordinate system because when we graph them on an x and a y axis, when we put them in a coordinate system, then we can use all the tools that we've learned to work with coordinates, all the formulas that we've worked with in the past, and we can apply them to vectors. And so that's kind of the benefit of taking a vector and placing it on an xy plane. So we typically place it so the initial point is at the origin. That's what the position vector would be. The direction angle of the vector is the angle formed by the positive x-axis and the position vector. So this would be the angle of the vector in standard position, which makes sense, right? Because standard position is kind of like that mathy way of measuring an angle. So if we wanted to figure out a way to write what this position vector was, then we have to figure out a way to write the horizontal component, how far it's going to the left and right, and how to write the vertical component, how far it's going up and down, because we know that the vector is the combination of those two things, left and right, up and down, and that gives you how slanted it is. That tells you how slanted it is. And another way of thinking of that is to describe how long the vector is, or how much magnitude it has, over what angle. Two different ways of saying the exact same thing. So what we're going to do here is we're going to tie those two ideas together. All right, so I'm going to label a few things in this picture. So this is W sub y, so this is the vertical vector. The vertical vector, it doesn't go left or right at all, and so the only component that it has is it goes vertically. I'm going to label it over here on the other side as well. So wy, and then this one, wx, I'm going to label it up here at the top. That length is wx, and then here this is the resultant vector, and I'm just going to label here, for the sake of the formulas we're about to write, that r is the magnitude of this vector. And remember, magnitude is just the length, okay? And I'm going to write this at the top because these are our notes. So if w, and I like to write this since I can't write in bold, so if vector w has magnitude r, then we're going to write some formulas. So the names of these sides of the triangle, this is the opposite side, if this is the angle we're talking about, this is the adjacent side, and then this is the hypotenuse. Okay, so a couple relationships I can see here is that cos would be adjacent over hypotenuse, and so cos theta would be w sub x over r. Sine of theta would be opposite over hypotenuse, so it would be it'd be w sub y over r. W sub y over r. So if I wanted to isolate this so I knew what just this vector was, or what just this vector was, I could take the r, the magnitude, and multiply it to the other side. So w sub x is r times cos theta. W sub y equals r times sine theta. And I drew this in the first quadrant, but we know that we could have drawn this in the second quadrant, we could have drawn this in the third quadrant, we could have drawn this in the fourth quadrant, which means we can get positive values and negative values depending on what quadrant we're in. And so I'm just going to put an absolute value around these to say these values could be positive, they could be negative, because all of the quadrants are going to work. So I wrote the absolute value because this works in all 4 quadrants. Okay. So we're going to kind of apply this idea. These are where these formulas came from, and we're going to apply this. We're going to find the magnitude, which means length, of the horizontal and vertical components for a vector with a magnitude of 8.3 and a direction angle of 121.3. So I'm going to draw a picture of that. So a magnitude of 8.3 is talking about its length. A direction angle is from the standard position. So we know that a 121-degree angle is like over here somewhere. Okay, so we'll say this is 121.3 degrees and that the length of this vector is 8.3. That's the length. Okay, so I can see that this vector is kind of slanted to the left. All right, and what they want us to do is they want us to find the horizontal and vertical components. So the horizontal component is this right here. It's how far to the left this vector goes. The vertical component is how far up this vector goes, because this vector goes left and up. So they just want to say how far does it go in each direction. So find the magnitude of the horizontal and vertical components. So they just want us to say the length of each of those components. How far to the left does it go? How far up does it go? So we're going to say this is vector v. So v sub x, the length of the horizontal component, is going to be r, the magnitude of the resultant, times cos theta. So 8.3 times cos 121.3. Now, this is going to give me a negative answer because this is in quadrant 2, and this goes to the left. But they're just asking for a length here. They said find the magnitude. So I don't care that it's going to the left. I just care to describe how long it is, which is why I'm going to put this in an absolute value. Okay, so if I type this in, and I don't need to type it in as absolute value, I just know that my answer is going to be positive. Again, we're talking about angles that are in degree measure, so I'm going to make sure my calculator's in degrees because I'm about to hit the cos button. And I've got 8.3 cos 121.3. I'm going to take my negative answer and make it positive because this describes a magnitude. So this is a magnitude of 4 we'll just write 3 decimal places. Okay, so that's the magnitude. Now, they didn't ask us to write the direction angle of this horizontal component, but we could write the direction angle, and the direction angle of this horizontal component would be 180 degrees. You can see it's pointing to where we know in standard position that's 180 degrees. So I'm going to write that for my notes. With direction angle 180 degrees. And if you think it through, your horizontal components would either have a direction angle of 0 degrees or a direction angle of 180 degrees. One or the other, because they either go left or go right. Okay, so next we're going to talk about the vertical component. So this is going to be v sub y. And so we're going to have 8.3 sine of 121.3. And this one's going to be positive because this is pointing up. the magnitude of this one, but again, you can put it in an absolute value sign because we know that the length should always be positive. 7.092 magnitude. And this one has a direction angle of 90 degrees. Direction angle. Okay, and if you talk about vertical components, they're either going to have a direction angle of 90 degrees or 270 degrees, depending on whether that vertical component is pointing up or pointing down. All right, so I just want to kind of summarize what we've seen so far. We've learned about vectors, and we know that vectors are directed line segments that represent the size of something, the number of something, which we call magnitude, but then also the direction of that thing. So whether it's velocity or acceleration or force, just the direction of that force or the direction of that velocity. And you can draw that in a picture, so it's very geometric, right? Where we can see the length of that, the size of that force and what direction it's headed, or the size of that velocity compared to the size of a different velocity and the way that that velocity is headed in a certain direction. But we can also take that information and we can represent it algebraically. And when we represent it algebraically, writing it out kind of in numbers and letters and things like that, we have two ways of representing it. One way is to talk about the horizontal component and the vertical component and to add those two components together, and together that makes up the whole picture. The other way is to talk about how long the vector is, talk about the magnitude of the vector, and then at what angle is it. So two different ways we can represent it on paper. What we did here is we represented it with trig. We talked about how long the vector was. We talked about what angle it was at. And then we use that to describe our horizontal component and our vertical component. What we're going to do next is we're just going to learn, well, if you have something written down, can you write just the horizontal component and just the vertical component in a way where you're not even really seeing what the angle is and what the magnitude is? And we want to see another way of connecting the two. So here we're looking at what is called the component form of a vector, which is written like this. So it says the notation AB, and notice these are not parentheses. They're like sideways V's, kind of. It's used for the position vector with a terminal point AB. The magnitude of vector V is written like this, V with vertical lines, and it's A squared plus B squared. So you can think of drawing like a triangle with that, and it would be the hypotenuse of that triangle. So if we look at this, vector V is -2, 5. So the horizontal component of this vector would be that it goes left 2. Overall, the entire vector goes left 2. The vertical component would be that the vector goes up 5. So when we look at the resultant vector, we're going to go from 0, 0 to -2, 5. And overall, that resultant vector has gone left 2 and up 5, but it's done it diagonally. So that's what that means. So it says find the magnitude, find the length of the vector, and then find the angle that would create that vector. So vector V has a magnitude of -2 squared plus 5 squared, which is 4 plus 25. So the magnitude of that vector is the square root of 29. And then for us to find the angle of the vector, we can do a few different things to find the angle of the vector, but what I think is the easiest is to use tangent. So if you can imagine this picture over here, if we create a triangle and we say that AB is this point, we have this horizontal component is A, here's that vertical component is B. I'm going to go ahead and label these in the triangle, A and B. And then over here is the angle in standard position. Then if I wanted to find that angle in terms of A and B, I can write the names of these sides. This is the opposite side. This is the adjacent side. So if all the information I had initially was opposite and adjacent, this is before I found the magnitude because I actually have the length of this now. But initially, all I have is A and B. I can actually find the degree measure of the angle from A and B. It's tangent. Tan of the angle is opposite over adjacent, which we always think of as y divided by x, or the vertical component divided by the horizontal component. So what I'm going to do to find tangent is, to find theta, is just take tangent of that angle. So tan of the angle is going to be the vertical component divided by the horizontal component. This is not an angle that's on the unit circle. It's not something that I'm familiar with. 5/2, -2 is not something that I've seen before on the unit circle. And so this is what I'm going to have to do in a calculator, which means that when I do this, I'm going to have to be careful to imagine where this angle is and think about it making sense for the vector -2, 5. So if I draw a little sketch of this vector has a horizontal component of left 2 and a vertical component of up 5. So left 2, up 5. So here is the vector, -2, 5. It has a magnitude of square root of 29, so that's the length of the vector, and this is the angle of the vector. So whenever I get an answer for theta, it should be some angle that's in quadrant 2. Now the answer I just got is -68.199. This angle is in quadrant 4. That's a quadrant 4 angle, which means that this is not the answer for the vector I'm talking about. So I need to go ahead and find the next tangent answer, and to find another tangent answer, we just add 180 degrees, or we add 1 pi. That was something that we learned in the previous chapter. So I'm going to add 180 degrees. I'm going to add half a circle, and that's the next angle that I get. And then I look at this and think, could that be a 111 degree angle? And yeah, that makes a lot of sense. So that means that theta is 111.801 degrees. So the magnitude is the square root of 29, and the direction angle of the vector is 111.801 degrees. All right, this says to write the component form, so write a vector like this, for a vector of magnitude 40 miles per hour with a direction angle of 330 degrees. So 40 miles per hour, that's your speed. Velocity is how fast something is going, and what direction. So we're going to say A, that horizontal component is 40 cos 330, and B is going to be 40 sine 330. So if we look at a picture of this, 330 degrees, we got 90, 180, 270, 315 is right in the middle, 330 is a little bit further. So our vector is over here in the 4th quadrant. So when I write my vector, my horizontal component is going to be positive, this goes to the right, but my vertical component is going to be negative because this vector goes down. So these are unit circle angles, so I'm going to be able to do this and get exact values. So 40 cos of 330 is √3/2. You might have that memorized. You might have to look at your unit circle when you do this. 40 sine of 330 is -1/2. So we've got 40 divided by 2 is just 20. So this is 20 square root 3. 40 times -1/2 is -20. So if we write this vector in the component form, we would say that its horizontal component is 20 √3. That's how far it went to the right. and its vertical component, excuse me, is -20. It went down 20. All right, now that we have our vectors written in this kind of algebraic form, they're a little bit easier to work with. So now we have vector operations like the scalar that we did before, but now we can do it algebraically. We have vector addition. We can add vectors together. We have vector difference. We can subtract them. And then we have the dot product, which is not multiplication, not adding. It's kind of both. It's a little different. It makes sense that it would not truly be multiplication, because if you think about how addition works and how multiplication works, when you multiply two numbers together, it's almost like you're finding an area, right? If you think back to when you first learned how to multiply numbers together, you were probably using little blocks, and you'd say 4 times 6 is 4 sets of 6, and you'd like lay the blocks out and you'd have 24. Well, if we look at vector addition, vector addition looks a whole lot like multiplication, where we have like some sort of width and some sort of length, and then we've got something over here that's building. So it feels a little bit weird to think visually of vector addition and vector multiplication, but the takeaway message from this is that there's not really any such thing as vector multiplication, or at least that's not what this is talking about. This is a little bit different than that. So there is some multiplication involved, but it also has addition, which just makes it a completely different story altogether. Okay, anyway, let's give these a shot. Let's try some of these. So here it says vector W and vector Z, and they just want you to subtract them. And this part, once we get into this algebra, this is a lot more intuitive. So if you have W and you're subtracting Z, you're going to have -3, 2, subtract 5, -1. And so all you have to do when you subtract, just like normal, is distribute the negative. So we have -3, 2, and we're adding -5, +1. So the resultant vector is -8, +3. Here we have a scalar for this one. It says -8 times z, so we can just put -8 in front of z, 5, -1, and then we're just going to distribute. So -40, +8. All right, here we have two vectors with scalar multipliers, and then we're going to add them together. So 3 times W plus 4 times Z. So that's going to be -9, 6, 20, -4. And when we add those together, we get 11, 2. All right, and then this one, the dot product, if you look at this, you can see you're going to consider the two different vectors, W, -3, 2, and Z, 5, -1. And what you do is you do the first A value, and here we go. They said the first coordinate, or the horizontal component from A, times the horizontal component from B, the vertical component from A, the vertical component from B, and then you add those together. So we're going to have -3 times 5 and 2 times -1, and then we're going to be adding those together. So -15 plus -2 is -17. That's the dot product. Okay, so next we're going to learn how to find the angle between two different vectors. If you draw two vectors as their position vector, if you draw them on a coordinate grid, how could you find the angle between them? Especially if you were just given the vectors in component form and you didn't know what the angles were. So this is the formula, and it includes the dot product. So cos of the angle between them is the dot product of the two vectors divided by the magnitude, or the length, of the first vector times the magnitude or the length of the second vector. So it says find the smallest positive angle between each pair of vectors. So it makes sense if you think about drawing two vectors. I'll draw a little picture here. They could say, here's one vector, here's another vector. If I discuss the angle between them, I could say that this angle is the angle between them, or I could say that this angle is the angle between them. And so they're just specifying here that the answer that we want is the little angle that's between them, not the large angle if you were to go, take the longest route. So that's all they meant by smallest positive angle. Okay, so to find the angle between two vectors, we're going to consider -3, 2 and 4, 5, and we just have to find the dot product between those first and each of their magnitudes. So the dot product would be -3 times 4 plus 2 times 5, so -12 plus 10. So the dot product is -2. And then we have to find the magnitude of each. So the magnitude of the first one is the square root of -3 squared plus 2 squared. So that's 9 plus 4. And then the magnitude of b is 4 squared plus 5 squared. That's 16 plus 25. 41. And so we would say that cos alpha is -2 over square root 13, square root 41. These answers could sometimes not be a decimal, but almost always are. So I typically do these on my calculator. So I'm going to type this in as a fraction. On the top, I have -2. On the bottom, I have the square root of 13 times the square root of 41. And so there's my decimal. I'm going to do cos inverse of that decimal, 94.969, 94.970. So the angle between them is 94.970 degrees. All right, we can try it again. So dot product and then the magnitude for each. So the dot product, A dot B, is -5 times 9 plus 9 times 5. So that's -45 plus 45. So that's 0. And then the magnitude of A, -5 squared plus 9 squared, so 25 plus 81, 106. So the square root of 106. The magnitude of B is going to be the same because it's just the square root of 9 squared plus 5 squared. It's the same. So here we have cos alpha is 0 over the square root of 106 times the square root of 106. And 0 divided by any number is just 0. So I've got just 0. And then if I do cos inverse of that, you should know this one because this one's on a unit circle. It's just 90 degrees. So those were vectors that are perpendicular to each other. All right, next we're going to talk about unit vectors. A unit vector is a vector with a magnitude of 1 or a vector with a length of 1. So here we have another form, another way to write vectors using the letters I and J. I is used for the horizontal component, so you can see that 1i is a length of 1, so that's a unit vector. J is used for the vertical component, and 1j is a unit vector. And so here they're saying write these components, these vectors that are written in component form, rewrite them as a linear combination of the unit vectors I and j. So now we have two ways that we're going to be able to write a vector algebraically. We have the component form, and then we're going to have linear combinations of unit vectors, or just the I and j form is how you can think of it. And it's very easy to write. So vector A is -2i, so the horizontal component has a length of 2, and so that's 2 units. And then plus 6j, because the vertical component is a length of 6. So 6 unit vectors going up. And then vector B is -4i minus j. So whenever you write vectors, you can write it in this component form, horizontal and vertical components, or you can write it in terms of its unit vectors. All right, probably the moment you hoped was not coming, but did definitely happen. We're going to do some application problems. So when we do applications of vectors, there's always a couple different ways of solving the problem. One way of solving the problem is to draw it out, think about the vectors in the picture here, and look at the resultant vector. And so then you treat the problem like you're doing vector addition. That's how I'm going to show you to do it. The other method is to think of the problem as a series of triangles and then use what you know about triangles to solve the problem. So if you had a right triangle, you could use SOHCAHTOA. If you had angle, side, angle, you could use law of sines. If you had side, 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 you could use law of cosines. That's another method. I'm not going to do that, and the reason is because if you do that method, then every single problem looks a little bit different. So but I do want to point out, and I am going to show you some examples of me working it out that way. And if you want me to make another video talking through some of the same examples and just using the other solution method, I can do that. You just have to send me an email. Okay, so here it says we have 2 draft horses that are pulling on a tree stump with forces of 200 pounds and 300 pounds. So here's our tree stump. We got the 200-pound horse. We got the, well, I don't know if the horses are that much, but that's how much force they're using. So 200 pounds of force, 300 pounds of force, and then this is the angles that they're pulling at. If the angle between the forces is 65 degrees, then what is the magnitude of the resultant force? So here is the resultant force, the force that we get when we add these two forces together. So what is the magnitude? And what is the angle between the resultant and the 300-pound force? What is this angle right here? Okay, so the first thing I'm going to do is I'm just going to put this right here on an XY plane. So that I can use math that I know how to use on an XY plane with this. So I'm going to write the vectors for B. I'm just going to call this vector B. I'm going to call this vector A. So vector A, and you can write this as the component form with those little sideways V's, or you can write it in the I and J form. It doesn't really matter. But this is our magnitude, 200 pounds. Our angle for A is 65 degrees. You can see from standard position, it goes up 65 degrees. So for A, I'm going to say 200 cos 65. So I've got magnitude multiplied by the angle. And then for the vertical component, I'm going to say 200 sine 65. Okay, and then for B, this would be a 0-degree angle because it's just my positive x-axis. And so I'm going to say that this is 300 cos 0, 300 sine 0. Okay, so the resultant force is going to be A plus B. So now I want to find the vector A plus B, which is what I get when I add these two together. So for the horizontal component, I'm going to add these. For the vertical component, I'm going to add these. So 200 cos 65 plus 300 cos 0, 200 sine 65 plus, sorry, that was, nope, that was 200. Uh, 300 sine 0. I'm going to go ahead and write out these decimal answers. So I got 384.524. And when I do this, I like to store this, and I'm going to store it as A. And then I'll type that in. Just going to copy paste this and switch the coses to sines. There's my vertical component, so 181.262. I'm going to store that as B. And remember, to store a number, I just hit STO down here, store, and then I choose a letter, and I chose A and B up here. Horizontal component, vertical component. Okay, and there we go. Okay, so for this resultant force, I just want to be able to figure out what the magnitude of that force is. So I have to do the square root of this resultant, so the square root of 384.524 squared plus 181.262 squared. And then I want to find the angle that's right here. I'm going to label this as theta. So square root A squared plus B squared. And the decimals are still on the screen, so if you didn't want to save them, you could go up and just copy paste them. So the resultant force is 425.105. So that means that if you had 300 pounds of force going this way and 200 pounds of force going this way, the resultant is that on the tree stump you have 425 pounds of force going this direction. That's what's happening. Okay, and then pounds of force. And then they wanted to know, well, what's the angle between these two, between the 300-pound force and the resultant. So I'm just going to do tan theta is the vertical component divided by the horizontal component. So these are two formulas basically that you should highlight or write down. This whole set of notes really has a bunch of formulas, but those two in particular are going to be really helpful, and they're from this page right here in your notes. So the magnitude of a vector is the square root of the horizontal component squared plus the vertical component squared. And then over here we wrote that to find the angle, you do tan theta is the vertical component divided by the horizontal component. Those are two very important formulas for being able to find some information. Okay, so I'm going to do this, and I just know that this angle should be smaller than 65, and it should, I don't know, if I was to guesstimate, maybe like 20 degrees or something, I'm not sure. Okay, so let me go ahead and do tan inverse of B divided by A. Hey, I was pretty close. 25.239. So the resultant force is 25.239 degrees above the 300-pound force. And the reason they said that, they're just giving you an orientation. They're just trying to tell you in relationship to what else in the picture. So we wouldn't say 25.239 in standard position, even though that's what it is. It's standard position because that's how we drew our grid. we put it there so that 300 pounds would be the positive x-axis, and so that that force, that vector would be exactly where we wanted it to be, so that we could use trigonometry and we could use our calculators. So this degree measure doesn't mean anything unless we've drawn this picture and we're describing this degree measure as the angle that's between those two vectors. We're not saying, oh, this is bearing or this is standard position. We're just saying this is the number of degrees between the two angles, or between the two vectors, I mean. Okay, we're going to skip this problem for right now and move on to the next one. So in vector application problems, it is very common to see problems that have to do with airplanes. Okay, so there's a few things that I wanted to point out when you're dealing with airplane problems. The first is that when the wind is at some angle other than the direction of the plane, which is like the majority of the time, some portion of the wind will either be subtracted from or added to the airspeed to determine the ground speed. So I think of, and I wrote this in parentheses, I think of the airspeed as how fast the airplane is trying to go. And then when the wind acts upon the plane, it might speed it up, it might make the plane go faster, or wind resistance might slow the plane down. So airspeed is how fast the plane is trying to go, ground speed is how fast the plane is actually going after the wind has had the impact. And then the other thing to consider is that the wind is going to cause the plane to travel on a course that's different from where it's headed. So when you have strong gusts of wind, they're going to push the plane a little bit off course. Not to say that pilots don't make up for that, but just whatever heading the plane has, the wind is going to have an impact. Okay, so here it says we have the heading of an executive's Learjet that has a bearing of 320 degrees. The wind is 70 miles per hour with a bearing of 190 degrees. Given that the airspeed of the plane is 400 miles per hour, like that's how fast they're trying to fly, find the drift angle, the ground speed, and the course of the airplane. Okay, so let's go ahead and draw pictures of this information. All right. The jet has a bearing of 320, so there's 270, 315 in the middle, 320 is a little bit further. So that's what that looks like. This is the jet. The wind has a bearing of 190, 180, 190. That's the wind. Okay, so if I draw a picture of this, I guess I could have drawn it all in the same. I like to draw my first two off to the side just to have a good idea of what I'm doing. So 400 miles per hour means that this one's going to be the longer. That's the vector for the jet. It's going to be the longer vector. Then for the wind, this is at this angle. It's going to be short because it's only 70. So 400 versus 70, here's the wind. So I've got one vector plus another vector equals the resultant. And so my resultant vector is going to be the jet plus the wind, and that's this one right here. So the jet plus the wind is where the jet actually goes when the wind is working on it. So the reason I draw this picture is just because it helps me to make sense of the answers that I'm getting. So I can tell that whatever angle I get for the jet plus the wind, it should be smaller than a bearing of 320. It should be a little bit less because the wind is pushing the jet down this way. It should probably be slowing it down. You know, this length looks a little bit shorter, so I would expect it to be going a little bit slower. And that's just going to help me make sense of my answers. If I get, when I do tan inverse, if I get an answer that's in the wrong quadrant, then I know I should add 180 degrees to get a degree measure that's in the second quadrant. So things like that are the reasons that I would draw a picture of this instead of just starting to write out my vectors and adding them together. So I'm going to go ahead and write the vector for the jet. I have the magnitude, and remember when we do this, we have to think in terms of math. So this is bearing, but over here now I have to start thinking in terms of math angles. So I'm going to have 40 or 400 cos, and then I can't use 320 because that's a bearing angle. I have to think of it in terms of math angles. So if this is 320, that means there's 40 degrees left to get to 360. And I know that this is a 90-degree angle. And so from standard position, this would be 130 degrees. So instead of saying 400 cos and then say it's bearing 320, I'm going to say this is the standard position of 130. 400 sine 130. Okay, and then for the wind, 190 right here. So I know this is 10 degrees. It was 10 degrees past 180. So if I measure it from standard position, then that would be just 10 degrees less than 270. So this would be for the wind 70 cos 260, 70 sine 260. Is the wind. And so then I can go ahead and find the jet plus the wind. So 400 cos 130 plus 70 cos 260, 400 sine 130 plus 70 sine 260. And I'm going to go ahead and store that as A. And then I'll type in for the vertical component using sine. Okay, so I've got them both typed in. I've got both of those decimals stored. Now I need to go ahead and find the magnitude. $359.032. So the magnitude of the resultant, the magnitude of what I just found, is the ground speed of the jet as the wind is acting on it. So this is the ground speed. Okay, and now I'm going to go ahead and find the angle. And so when I solve this, when I do tan of the vertical component divided by the horizontal component, I'm going to find this angle right here, and it's going to give me that angle in standard position. But to write it in the context of the problem, we don't want to do standard position. That's thinking XY coordinates, which the people in here aren't. They're thinking in terms of bearing. So I'm going to get the answer in standard position, and then I'm going to have to convert it back to bearing. Okay, so I'm just going to write tan theta is the vertical component divided by the horizontal component. And I'm going to make sure that this angle that I get is a quadrant 2 angle. So tan inverse of vertical divided by horizontal, negative 41. That is not a quadrant 2 answer. This is a quadrant 4 answer, and so I'm going to have to add 180 degrees to make it a quadrant 2 answer. Okay, so 138.590. So I'm going to go ahead and use a picture to help me convert this to bearing. So this is 138.590. Okay, so to figure out what this is in bearing, there's a few different ways I could do it. I could figure out how much this is and subtract it from 360. That's one option. I could figure out how much this is and add it to 270. So there's always a few different ways you could get your answer and convert it to bearing. I'm going to go ahead and do the route where I figure out this little bit and subtract that number from a full circle. So 138.590, if I subtract off 90 from the first quadrant, then I can see that this little piece right here is 48 degrees and 48.590. I'm going to stop. It's almost 49 degrees. So I'm going to take that and subtract it from 360 so that I can write that answer in bearing. So 360 minus this. There we go. So this is bearing 311.410 degrees. 410 thousandths. That's how you would say that decimal. Okay, bearing that many degrees. So we've got the ground speed. We have the course of the airplane. The airplane is bearing 311.410 degrees. We want to find the drift angle. So the drift angle is just how far off course did that jet drift. So it's bearing 311.410. It was supposed to be going 320. So the drift is just where it was supposed to be going, and where it went and what's the difference between those two. So 320 minus 311.410. 8.590. So the drift angle, 8.590 degrees of drift. Okay, now here's what I said I was going to show you, but I'm not going to make you do. If you look at the example that we did, this is the same example I did before, but this is me doing that example using triangles. My first set of information was side angle side, so I started off with the law of cosines, and then I switched to the law of sines. I ended up using the ambiguous case, and so when I solved for the missing angle at the end, I just made sure that I wrote the two different possibilities for the angle to consider that ambiguous case, and then I knew that the second version didn't work because the angle was too big. So you can do this problem the way that we did it by finding the two vectors and just adding them together, or you could use triangles. So law of cosines, law of sines. For this second one, you can also, same thing, use law of cosines, law of sines to do this problem as well. So I had to find the angle between the jet and the wind, and then I was able to use side angle side information, and then angle side side information to find the result at the end. So you can always use triangles to solve it. You don't have to do vector addition if you don't want to. Now, the reason we skipped the other problem is because vector addition doesn't work to solve this problem. It's a very simple problem. This one uses SOHCAHTOA. So what I decided after I made these notes, printed out copies of them, I decided that I don't want to overwhelm you guys, and so I decided to focus in on application problems where we could use vector addition and the resultant vector to be able to do the applications. And then if you want to use triangles to do the applications, then that's fine, but I'm going to let that be something extra that you do on your own. So I'm going to look specifically for problems that can be solved, like the way that we did this one. Not that method though. I'm going to look specifically for problems that can be done using this method and for problems that can be done using this method. So writing down the two vectors, adding them together, and then this kind of straightforward process. That's what I'm going to look for. But I did want to point out that these problems, you are drawing triangles and you can solve them using triangles as well.